All right, so let's continue our notes. We're going to continue with lesson 1.3, average rates of change here, and then we're illustrating with an example about a car traveling 110 miles per hour, 110 miles in 2 hours, which we know intrinsically is 55 miles per hour. We know this just kind of on by reflex. So when we were talking about stuff like that, we see instantaneous rates of change while we're driving, okay? But the average rate of change is something totally different, and it's kind of something that we are familiar with. So let's take a look at some ideas about limits and calculus and instantaneous rates of change that require you to have a good understanding of the average rate of change. So here's a graph of our example with our driving here. And notice that we kind of have like a step function here where we're looking at the time in hours since 8 a.m. And each time we're moving at a particular rate. And this is a particular example about suits made, suits produced at a company, Rags Limited. So if we take a look at this, I've taken the time to write in the hours so that it makes kind of better sense. Otherwise, 1, 2, 3, 4, we might lose track. So they want to know how many suits were made from 9 a.m. to 10 a.m. So if we look from 9 to 10, our interval, our coordinates are denoted by hours and then suits made. So for every hour, 20 suits are made. So between 9 and 10 a.m., it shows we've got a bend here. But remember, we're always looking for this secant line. So when we take a look at this, we can tell really quickly that there are 35 suits made between 9 and 10 a.m. It's a little more than 20, yes. But at this point in time, within that first hour, 20 were made. Within that second hour, 55 were made. So you can tell that the difference between the first and second hour has to be 35. Hence our answer. Okay. You've seen this before. We call it slope. We even used it in the last section to graph. So, but this is going to be a subtle change in how we think about slope. All right, let's continue with example number 2. We need to know the average number of suits produced per hour from 9 a.m. to 11 a.m. So again, that's very simple. From 9 a.m. to 11 a.m., we can see at 11 a.m. they made 64 suits, whereas at 9 o'clock they had already made 20 suits. So that means we have 44 suits, and then if we subtract the hours on the denominator and divide, we get the number of suits per hour. Okay, I'm pretty sure we're comfortable with these kinds of things, but let's continue. As you can see, I had made some mistakes in my writing, but I had to make sure that it was right for you all. Just doing a couple of quick check problems. We want to take a look at what we'd have as an average rate of inches per hour. If it rains 4 inches over 8 hours, that's going to be half an inch an hour. If you travel 250 miles on 10 gallons of gas, that means you went 25 miles with 1 gallon. And if your temperature is dropping from 82 degrees to 76 degrees between 2 p.m. and 5 p.m., that means it's dropping at a rate of 2 degrees per hour. And it's negative because it's dropping. So some things that we need to know about slope. We need to recall when we're talking about inputs, 2 inputs, there needs to be 2 outputs. And so if we're talking about a change in x, well, this is our equation. And if we're talking about a change in y, change in our outputs, this is our function. But remember, when we talk about our y outputs, we can always write them in terms of f of x notation, which leads us to our formula that you've seen since high school, where we have the slope being y sub 2 minus x sub 1, x sub 2 minus x sub 1, and these two cannot be the same, otherwise it would be 0 and it would be undefined, it wouldn't exist. Okay? All right, so that leads us to another one of our graphic examples. This is the secant line. When we look at this, you can see that if we substitute in the f of x notation for our y sub 2 and our y sub 1, we end up with this notation, which really is indicating the difference in x's here on a curve and the difference in y's, okay? And so when we're finding the slope, we're also finding the secant line, which is the average rate of change. So this is interesting. This is tying geometry in with our algebra. So let's take a look at an example. Here we have a parabola, so some portion of the curve is illustrated here. And we're going to be looking at a couple of different areas where we're changing from 1 to 3 and when we're changing from 1 to 2. So if we take a look at this, first of all, we want to find the average rate of change when x goes from 1 to 3. So from this point to this point, pretty steep. So let's take a look. So we know this. We've been given x1 and x2. And we should be able to figure out what y1 and y2 are. When we substitute in f of x sub 1 and x sub 2, once we plug that in, we get 2. So when x sub 1 is 1, we plug it into the function, we will get 2. For the second x value, if we plug 3 into the function, we will get 10. Now we have y sub 2 and y sub 1. We can use our average rate of change formula, aka the slope, and we'll find it to be 4. For part B, we're going to do the very same thing. Take a look. We're going to have an x sub 1 of 1 and an x sub 2 of 2. We'll find our y sub 1 and our y sub 2 by plugging in these values for x into our original function. And that's how we end up with 2 and 5. We then take 2 and 5 as y sub 1 and y sub 2 and subtract using the slope formula. And now we found 3. Okay, so that's finding the average rate of change. Let's go on to our next set of notes here, where we are doing a quick check. I'm going to let you look at the quick check for a few seconds and see whether or not you have any questions. Okay, it should be pretty clear. Let's move on to our difference quotient as the average rate of change. And now this is where things start to get just a little scary. So we're going to have some notation because throwing around those x sub 1s and x sub 2s and y sub 1s and y sub 2s is very cumbersome. So a mathematician has taken it upon themselves to change the notation so that we can use the different quotient. Okay, so we'll use x plus h for our x sub 2, and for x sub 1, we'll just use x. Okay, so you got to keep that in mind every time we're doing these problems. Okay, so that leads us to an example. So, of course, there's always a definition, but that's just the definition of the difference quotient. Let's take a look. Here we are, we're given a function x squared, f of x equals x squared, and we need to use the difference quotient to figure out what we'll get for our slope if we use x is 5 and h is 3. Keep in mind, we are using the formula directly from the definition. We're using the formula. Plug in your x and your h into your equation, and you'll get your slope. Okay? This should be a pretty close situation, and then you'll figure out that the points that we had, 525 and 864, those are our coordinates on this parent function of the parabola. Okay, and so we just kind of found our slope, average rate of change, on that curve. Now I've left B and C for you to do so that you can practice. Okay, and that leads us to another example, example 5. Let's take a look at that, example 5, where we're going to find a simplified form of the difference quotient and then evaluate the difference when we have x equals 5 and h is equal to 0.1. Okay, so if we take a look at that, and we've also got one for when it's 0.01, but I'm going to leave that one for you, okay? So in this case, we know that f of x equals x squared, and it has this coordinate x and f of x, aka x and y. And of course, we're now going to use the simplified notation for the second point, where we'll have f of x plus h equals x plus h squared. Okay, so then of course, since we're using this function, this is the function x squared. So if we're using x plus h, we're just going to have x plus h squared. Okay, and if we do our factoring, we should end up with this equation, x squared plus 2xh plus h squared. Now, if we directly use the difference quotient formula, plug in what we know, this is what it's going to look like. It's kind of scary looking, but really not. If we just keep our cool, it'll be okay. So you think about this. The x squareds will cancel each other out and leave us with 2xh plus h squared over h. And if we factor out an h, we've got one here, we've got one here, factor it out, we can cancel and end up here. Now it's really easy to evaluate when x is 5 and h is 0.1. Pretty sure you could do it when x is 5 and h is 0.01. That should take no time at all. And remember, we should always make sure that the h is never 0. All right, here's another example for us. Here we have an x cubed function. You probably want to just write this one down because the time it takes to multiply x plus h cubed is kind of time consuming. But this is what you'll end up with. Okay, and again, if we plug all of that back into our difference quotient formula, we should end up here. Our cube functions will cancel. We'll end up with this particular function. Of course, we can factor out an h because look, there's an h in every term. Factoring it out, they cancel, and we're left with this function, and now we figured it out. All we did was find the simplified form of the quotient, a difference quotient formula, okay? And of course, I left a couple of problems for you to do. The quick check and these two problems here. They'll be done for you when you get to class. You can take a look at them, or you could try them out for yourself. And then tomorrow, Monday, we will start with 1.4 and 1.5. Thank you, and have a good weekend.